Hello everybody. In this video we are going to look at example or exercise 2a on page 161 of the workbook. And the problem asks us to start with a vector field. So they're giving us a vector field and then they're asking us to use Stokes Theorem to find a line integral where C is a circle parallel to the yz plane of radius a, centered at the point on the x-axis and oriented counterclockwise as viewed from the positive x-axis. I have to say they don't give us many details, so we just have a general radius a, and we just have a point on the x-axis, and we have an orientation as viewed from the positive x-axis. So this is what they're telling us. Let's draw and see what this looks like before we go ahead and compute this line integral. So let's draw. Here's my coordinate system. So our curve C is a circle parallel to the yz plane. So here's y, here's z, here's x. Parallel to the yz plane, radius a centered at a point on the x-axis. They don't tell us the point, so I'm just going to pick one. So here's my point on the x-axis, and they don't tell us a radius, so I'm just going to pick a radius. Let's just draw a circle. So here we are. This surface is my surface S. And the curve around it, this is the circle that they were telling us about. So this is C. And we don't have an orientation yet. They say the orientation is counterclockwise when viewed from the positive x-axis. So imagine we are looking down from over here. This is my eye. I'm looking down the x-axis and I see counterclockwise motion. So that would give us this orientation right here. So moving around counterclockwise. And this is going to be important in a minute. So this is what we're looking at. They are asking us to compute a line integral of f dr. But they're also telling us to use Stokes Theorem. And so Stokes Theorem says that instead of a line integral, you can compute a flux integral over a surface S of the curl of f dA. And so the surface S, I already labeled it. So S is the inside of our circle right here. And to compute this flux integral, our surface needs an orientation, and the orientation needs to fit the orientation of the circle using the right-hand rule. And if you do that, in the example so far, we've always done it the other way around. We had an orientation for the surface and then found the orientation for the curve, but you can also do it the other way around. So imagine drawing in a normal vector. It has to point in this direction right here, in the direction of the positive x-axis, so that when you curl your fingers according to the right hand rule, you match the orientation of the circle. So there's our normal vector pointing into the positive x-axis, and so we can write down what n is. N has to be I, because it only has that x component. It only has the I component in the x direction. All right, so we just figured out what dA is. dA is n dA, and we still have to compute the curl. All right, I wrote down, so we still have to compute the curl. And I wrote down the formula of the curl right here. So we have to figure out partial f3 partial y going to our vector field. So our vector field, I'm going to write that down here. That is minus 2yi plus 2xj. And we want to find the curl of that vector field. And so we are starting with partial f3 partial y. Well, there is no f3, or rather f3 is 0. So that gives us a 0. Then partial f2, so we have 0. Partial f2 partial z, well, f2 is 2x and f1 is minus 2y. So partial f2 partial z is also 0. So I just have 0i. Then what happens to j? Partial f1 partial z, well, minus 2y, there are no z's right there, so that gives me another 0. Minus partial f3 partial x, well, we didn't have, or rather f3 was 0, so that's another 0. Well, let's see if we get anything for our third component. We have partial f2 partial x. All right, partial f2 partial x, that's actually something non-zero, that is 2. And then minus partial f1 partial y, that is minus 2. So we have a total for the curl of 4k. That's nice. That's pretty simple. So we computed our curl. We can plug it into our integral. We have 4k. And then dotted with n dA, and we decided that the normal vector to our surface n is I dA. And okay, well, we find the dot product of 4k with I, that is 0. So our integral is just the integral over 0 dA, never mind what the surface is. Didn't matter what the radius was, it didn't matter where our circle was centered. Apparently, for any such circle in a plane parallel to the yz plane, the surface integral is 0, and therefore the line integral is 0. Okay, go ahead and try example B, exercise 2b, and then you can read the solution in the workbook.